yes, so we've had already many great talks about SLT from an applied perspective. So how these tools, which were developed by Timaeus and others, are useful for interpretability. And so the goal of this talk is to give an overview of the theory that sort of led to this and how it's connected with some question in singularity theory. So I'm going to very quickly sort of give the one pitch for that. I mean, that's been already covered very well in Jesse's talk for why this SLT is relevant to interpretability and hopefully to alignment. I'm going to explain the sort of set the stage for a bit of Bayesian statistics. I'm going to explain why singular models are special and introduce this local learning coefficient, which is a measure of how special they are. I'll present these main results of SLT, so these results about the Bayesian statistical learning theory for singular models. I'll say a little bit more about this local learning coefficient and about its geometric meaning, and if I have time, I'll say a little bit. But this is more technical, maybe topic. So okay, one slide summary of what Jesse has been explaining in this first talk. So one aspect of alignment and safety that seems very central, certainly to me, is the problem of generalization to out of distribution data. And generalization depends on the structure of the learned model. And one of the key properties of machine learning models in general and neural network in particular is that they are degenerate. There are many ways that they can achieve a low loss, and so there is an internal structure to the model which is selected by the training process and by the inductive biases. And so we want to understand all of that, and so there is this sort of S4 correspondence and so we wrote with many people here. We wrote this position paper that spells this case in a bit more detail. So what does that has to do with singular learning theory? Well, singular learning theory has provided this. First of all, a theoretical framework, which is due to the Japanese statistician Sumio Watanabe, which sort of connects in the context of Bayesian statistics the loss landscape geometry and generalization and other things. And starting from this theory, you can actually extract from the theory an estimator of the geometry of the loss landscape. So this local learning coefficient via using stochastic gradient MCMC method. And then, as you've heard in many talks, if you've there are sort of refinements of the local learning coefficient, in particular this notion of susceptibility, which sort of goes deeper into the structure of in the structure of the model and the data. And this can all be justified or through analogies with statistical physics. So it's really a good foundation, a good starting point for this kind of approach to this idea of developmental interpretability of models. And it works, so that's maybe the most important thing. So again, if you've been to those talks, you've seen examples of how these methods can see both behavioral and internal model structure, and that it does seem to in some experiment to measure model complexity, generalization, and and going forward, we hope that the finer geometry of the loss landscape will lead to finer insight into the structure of the model and the data. And in particular, you can go to Will's talk tomorrow on programs and I don't know if it's program as singularities and this idea where we'll in particular explain this idea of structural Bayesianism. But okay, so how much theory do you?
So going back a slide or two. So if we say that we're one forward, if we say that it's relating kind of complexity to generalization in Bayesian statistics, in one anomaly work, is this still referring to kind of in-distribution generalization? Like you have a training set and then you want to perform on future examples from the same distribution, or is it saying something else?
The starting point is about the in-distribution generalization. But we can hope, for instance, using this notion of susceptibility to capture out of distribution via chain deformation of the data distribution.
SLT, generalization does refer to kind of in-distribution.
Yes. Okay, so okay, you've come to this talk, so you want to learn something about SLT theory, but it's maybe unclear how much you need. I mean, the first point is that this applied singular learning theory has been I think very successful, and it's blossoming. But to understand it, you don't really need all this fancy theory. I mean, you just have to take this recipe. So you just sample from the Bayesian posterior, you compute expectations of observable, and then you try to interpret that. And in some sense, and of course, you can this can be justified, I think, by some pretty compelling analogies with statistical physics, and maybe then that's all you need. The next problem is that, of course, SGD training is not Bayesian, and so it's unclear what SLT is telling you directly about the inductive biases of stochastic optimizers. I think there are many good reasons to expect that SGD, both empirical and theoretical, to expect that SGD is affected by the degeneracy in the loss landscape. But it's unclear how that compares with the effects on the Bayesian posterior. And the other one is, it's also unclear is if this large data limit, this sort of overparameterized regime, is the relevant regime for modern deep learning. So, but I think SLT still gives a very compelling, and maybe the only example that I know of statistical learning theory, which really, for a very general class of model, ties together the geometry of the loss landscape and generalization. I mean, another reason to study this theory and to study the sort of singularity theory is that compared to the landscape, I think the physical analogy, the analogy to statistical physics, maybe only goes so far, because the loss landscapes that we encounter in deep learning do seem to be qualitatively different from the ones that occur in statistical physics. Roughly because models in statistical physics are kind of simpler than the structure in complicated natural data distributions. So it's kind of maybe useful to think about the singularities of complex loss landscapes. And and also without theory, it's kind of unclear what this applied pipeline sort of, what information this applied pipeline gives you. So, okay, so now I will sort of introduce some notation for what we're going to do. So, don't worry, I'm going to go through most of these things in more carefully, but those are some of the main actors in the sort of Bayesian part of our story. So first we have a model, and in this context, of course, in this sort of theoretical context, we actually start with the data generating distribution, which of course in practice we don't have. We start with then we generate a data set, and this here in SLT, and this is one of the main assumptions that Watanabe does, and that is that we look at IID data. We have a parametric statistical model, which and a prior distribution. So because we are Bayesian, so and from this model, you can derive a sort of loss functions, both sort of empirical and population loss functions, a Bayesian posterior, and associated to this posterior distribution, there is a partition function and this Bayesian free energy, which Jesse already discussed. There is a predictive distribution and quantities which, like statistical learning quantity, which measure how well the model is doing. So in particular, the Bayesian generalization error. It's, now going to describe some of these things. So, I mean, here I have 4 functions, but there's essentially 2 of them. So, because first of all, I have the empirical loss function, also the cross entropy between the sort of empirical distribution and the model. I have the population loss, which is the cross entropy of between the true distribution and the model. So it's the expectation of the. But then I can sort of normalize this function, and for theoretical purposes, it's sometimes useful to look at, instead of the cross entropy, to look at the KL divergence or the relative entropy. So it just amounts to subtracting the sort of empirical entropy or entropy of the true distribution. So this Bayesian framework, so as I introduced it, and as Watanabe discusses it, is about sort of density estimation. We have a probability distribution on some sample space, and we're trying to learn it. But as a special case, and maybe the most relevant for sort of basic machine learning, we want to do supervised learning. And in this case, we have a data set not consisting not of point but of pairs, and we extract some functional relationship. Let's say there's some unknown function, and there's some Gaussian, some noise which we just assume to be Gaussian, and then we can reinterpret this as we can put this. We can reinterpret this in probabilistic term as the true distribution being of this form, and then the model being also of this form for some parametric function, and then we recover the usual mean square loss function and.
So Q is the true distribution that is the parameter.
Yes.
So why do we think that PX is
because, well, I guess one reason is that PX or QX does not matter so much, because we're trying to learn the conditional, and you could imagine that you're in a situation where you have a lot of X data, and so you sort of know what the distribution of X's are just because you have access to a lot of X data, but you don't know the associated labels. Okay, so in this situation, we can introduce the space of optimal parameter, the spaces of where the loss is minimal, so W0s, and there are 2 cases, right? Either the model contains the distribution that the true distribution, or it doesn't. So if it does, we say that the model is realizable, and as well as it's unrealizable. One nice feature of the realizable case is that then W0 becomes just the set of minima of the set of zeros of this function K, of the KL divergence between the truth and the model. And I'm mostly going to assume that we are in the realizable case. I mean, there are extensions of the theory to some unrealizable settings, but it's a bit technical. So, and
again, it's the function of the parameter.
Yes, yeah, it's this function. Does it? There's no. Is a pointer on this? I don't think so. Okay, so now let's go Bayesian. So we introduce the Bayesian posterior, and I mean, in some sense, from the physicist's perspective, the main quantity in this story is the partition function, and the associated free energy. So the partition function is basically the probability of the data according to our prior and our model, and so you can write this as this. Integral of the likelihood, or in this form where you put this cross entropy, and this is the form that's sort of most useful for the sort of the connection with later with singularity theory. The free energy is just minus log of the partition function. We can also define a sort of local free energy, and this is kind of useful for this story of, for instance, Bayesian phase transition that was also discussed in Jesse's talk. And then the Bayesian posterior distribution is this the base rule is this quantity or this distribution. Okay, so then we want to predict things. So in the Bayesian framework, you use the posterior distribution to create an ensemble of model and make prediction like that. So you just average your model according to the Bayesian posterior, and so that's the predictive distribution. Sorry, there should be a star here. And then you can just look at the average loss on the training data. So that's the Bayesian of that predictive distribution. So that's the Bayesian training loss, and the average loss on a new data point. That's the Bayesian generalization loss.
What is the star?
It's yeah, maybe yeah, I'm not sure. It's I think it's just to sort of break the uniformity, because otherwise everything is called P of something something. But, yeah, no, there's no. Yeah.
Like the found like probability, like the parameterized probability that minimizes loss or something.
It's not
Yeah.
Like minimizes training cost.
Yeah, but no, it's just about the notation is. Yeah, I'm not sure. I know you can remove the star if you want in your mind's eye. Okay, so now let's talk about regularity and singularity, which is the key new ingredient in singular learning theory compared to the classical Bayesian statistics. So the sort of key observation is that machine learning model, in particular deep learning model, have this property that they often degenerate around learned parameter, in the sense that there are many changes of parameters which leads to very small or no changes in the model. Actually, it should be P of X maybe. And so the guiding hypothesis, which is really, I think, justified to some extent by SLT and by on the one hand by SLT theory and by the empirical work that has been done so far, is that this degeneracy, first of all, it arises both from sort of the global constraint on the architecture of the model, but also somehow throughout the training, or it changes throughout training. It reflects these changes in degeneracy reflects how the model learns the structure of the data. It is correlated with generalization, and it can be, maybe most importantly, it can be measured through these responses of observable to perturbation. And here I should have put susceptibilities, or LLC and susceptibilities.
Sorry.
Yeah.
So you already mentioned two different kinds of degeneracy. One here, where changes in W lead to no change in the model.
Mm-hmm.
Also, changes in W lead to no change in the loss. Are those meaningfully different noises of degeneracy, or is that actually the same?
Well, so for instance, in the realizable case, this is the same, because you are at the minimal loss. Changes in the loss are, and this is a good question. In particular, when you start to think about SLT in the unrealizable case, you have to make to develop the theory, you have to make an assumption that these two things are not too different. The two things that you've said are not too different. But no, it's an important point. Okay, so this is one way to measure the degeneracy, and I think the way that hello? No, it's just present. So one sort of way to measure degeneracy is to look at the spectrum of the Fisher information matrix, or the spectrum the spectrum of the Hessian of the loss function. And what people have in deep learning have noticed, and have studied empirically quite a lot, is that those matrices tend to have very many small eigenvalues throughout training. And so that's one indication that during training you are in some sense very very close to critical points, or at least in some very there is some very strong anisotropy of the model that is an indication of degeneracy. Yeah. But so here's a sort of simple definition, sort of capturing the difference between regular and singular model. So a model is regular if, first of all, the loss has a unique minimum, and if this minimum is non-degenerate. So this Hessian matrix here is a positive definite. So here in this definition, we only care about what happens somehow at the end of training. So this is really about the situation at the minima of the loss function, and this is because we're interested in this sort of asymptotic statistical learning, or that's what the theory is going to be able to quantify precisely. But of course, in deep learning, or in application to deep learning, we also care about somehow the structure of other critical points of the loss function, or the other degeneracy of the loss function. But for the theory, this is what we can talk about.
So just to make sure, here LW has to actually be a global minimum. So if you have a model that has a bunch of local minimum, the locally convex surrounding minimum, local minimum. That is not a singular. That is a singular model, but not in kind of the using way.
Yeah, it's a very simple example of a singular model, and yeah, then the theory will tell you something about how this differs with regular model. But
like a local unit here and all else like unique global mode, then it can be regular.
Yes, yeah. Yes, that's why it's really about. This is really a definition about just the bottom of the loss landscape. So in the realizable case, actually these two matrices are the same at the bottom. So yes, in this case, yes. Otherwise, it can be different.
This definition is equivalent to the parameter to probability injective.
It's a kind of it's only asking for the injectivity again at kind of at the bottom of the loss landscape. Yeah. So you could have. Yeah.
What is realizable?
Yeah. So realizable means that the true distribution can be realized in the model. Yeah. Okay. So where do which models are singular? Where does singularity come from? So, first of all, deep learning models, they are typically over-parameterized in some sense, and also they admit many sort of symmetries. There are many symmetries of the parameters that don't change the function. So an example of discrete symmetry is just permuting neurons in a layer, for instance. But there are, for instance, ReLU networks that have these continuous symmetries, which have, yeah. And the point is that continuous global symmetry induce what I would call generic degeneracies of the model, generic singularities of the model. Basically, this is the situation where at every point in the model, there is a way to change the parameter which does not change the function, sort of uniform way. But you can also have the situation that specific parameters can have sort of additional special symmetries or special degeneracies. And one example could be sort of dead neuron in a ReLU network. Well, it's a neuron which, because of the on the data, is like the input is always negative, so the ReLU always returns 0. And then you can change the weight quite a bit around that, some of the weight quite a bit, and still don't change the function. So most machine learning models are singular, and basically anytime you have features, anytime you introduce some complicated structural features in a statistical model, you introduce degeneracies, symmetries, mixture models, hierarchical structure, compositional structure, latent variables, and so in particular neural networks are singular. So I'll just present a toy example of this. So the case of a normal mixture so this is the case where you have two parameters A and B. This is a mixture of a normal distribution centered at 0 and a normal distribution centered at B. And I take the realizable situation. So the true distribution is like this. So I just wrote the function. The point was just to make the point that even for very simple model, the sort of the analytic form of the functions that you get is complicated, and it's not clear how to sort of extract useful information from this. And one thing that singular learning theory tells you is somehow how to extract maybe some interesting information from that. So there are two cases, right? If neither these true parameters are 0, then actually the Fisher information matrix is invertible. This point is identifiable. You can recover A and B from the model, and the model is regular. But if one of them is 0, then actually the matrix, the Fisher information matrix is not invertible. The point is not identifiable because what happens is that on both you have two sides of the square which give it the same model, because the mixture degenerates to a single Gaussian. The set of optimal parameter in this case is the set of the two sides of the square, and all those models are singular. And basically what singular learning theory suggests is that, for instance, if the true distribution was literally at 0, 0, then what the theory tells you is look at the singularities of this loss function, and in this case it would mean look at this second order term in the Taylor expansion. And from this from this thing you can predict some of the asymptotic statistical learning theory as in the large data limit. In what sense? No, it's not. It's not a symmetry outside. I mean, it is a symmetry when one of them is 0. Yes, but not outside of that. Okay, so I mean, one concern with I don't think maybe people in this room will necessarily share, but I think for statistician it's kind of something that comes up quite a bit is that, I mean, every model can be made regular by some small perturbation. So in particular, if you perturb the truth, you can make, well, this is a little, okay, yeah. Well, basically, if you allow small perturbations of the truth and the model, you can definitely make your model regular. So it's unclear if, from that perspective, singularities are statistically relevant. But the point is that even if you're close, I mean, if you're a regular model but you're close to a singularity, then actually you'll be certainly in the Bayesian case, in the Bayesian setting, you basically behave like a singular model for a very long, for a very large range of data, number of data points. So this is this for this normal mixture. So here is the true distribution, and this is the Bayesian posterior for 1,000 sample. So even for the very this two-dimensional model, you see that, I mean, this is not a Gaussian, right? This is clear enough. Those are different, just realization of the posterior, because the posterior is a random variable depending on the sample data. Yeah.
I think the point here, right, is that A star times B star is not 0.
Yeah.
0.08.
Yeah.
Whatever. It's good, so it shouldn't be singular. But actually, look at these long, flat directions that you can kind of coast along for a long period. Like in the top right panel, it looks pretty degenerate.
Yes.
Even though it's not precisely singular.
Yes. Yes.
Different sample size of 1,000 from this model give really different posteriors. That's surprising. 1,000
Yeah, but no, but that's. Yeah, that really shows that these singularities do have a pretty strong effect even in this case. Okay, so now let's try to quantify this degeneracy. So and so I'm going to introduce this learning coefficient, which is sort of in SLT the first way that we have to quantify degeneracy, and it's kind of natural to try to do this by looking at the volume of low loss, I mean the set of low loss parameters. So the volume of sub-level set of the loss function. Yeah, basically the points where we allow the loss function to go up to the minimum plus epsilon. And it turns out that for nice functions, so for instance for piecewise analytic functions, let's say, where you have to define what piecewise means precisely, but this volume function always has the same kind of asymptotic behavior as epsilon goes to 0. There's always some constant times epsilon to the lambda times minus log epsilon to some mu minus 1, where lambda is some positive, actually positive rational number, and mu is an integer. So the learning coefficient of our model is this exponent lambda. So this is somehow yeah. Yes. Yeah. I mean, maybe I should directly jump to a picture. No, you know. I mean, I'm going back, but just so this is for various. So what you do is you look at the values for various epsilon, and the volume here is actually the volume of this disk in this case, right? Okay, going back. Yeah, so this. So as a yeah. So mu is just some integer. Is called the multiplicity. It's kind of a secondary invariant. Yeah, it for the moment in the application it doesn't play a role, but it's kind of there. So you
RC alpha and
well, so okay, so if in this case, okay, if they are, but I mean basically C is very hard to compute, and it sort of also depends on the global geometry or so. But yeah, they are unique. Yeah. So there is a local version of this story. So because okay, as I should have made more explicit. So for singular model, this set of optimal parameter W0 is not one point. I mean, usually it's some complicated manifold, or in fact analytic set. And so there are many optimal parameters. There are many good solutions, and we're sort of interested in distinguishing them. That's where we started with this idea of inductive biases, and so there is a local learning coefficient which measures the same quantity, but when we localize around a small neighborhood of a particular point. So you have to take the thing small, the neighborhood small enough that you don't get the behavior from some other point, but as long as you take a small enough neighborhood, you get this same kind of asymptotic with a well-defined local learning coefficient. So for regular model, this I mean, there's only one W star, and the global and the local thing are equal, and they're equal to D/2. And that's just because of the volume of spheres, the way that the volume of a sphere depends on the dimension. For singular model, this local learning coefficient is always less or equal than D/2. And you should just just keep in mind that a small local learning coefficient means more degeneracy.
So it doesn't involve cases where the model is singular, but the local learning coefficient is exactly D/2.
No, if the local learning coefficient is exactly D/2, then actually you are at least locally regular. Yes, you are. But okay, there is something still interesting to say in that direction that I will mention later. Okay, so the reason that I think that this definition is maybe the most intuitive in terms of what kind of degeneracy means. It's telling you that the space of parameter with low loss is very big. That's what degeneracy means. But from the Bayesian story, what is important is that the same quantity controls the asymptotic of exponential integrals. Because this integral looks suspiciously like the integral defining the partition function. The only difference is that here I've replaced ln by L, and L is just some some analytic function. Then the behavior of this integral is also as n goes to infinity. So as in our case, the number of data points goes to infinity, looks like this. And okay, maybe ignore this bit. The important thing is this n to the minus lambda, and there is a local version as well. So it's the same quantity that controls both. Yeah. I think it still works, but I mean maybe sub-analytic. I mean, yeah, but yes, yes. And so in the analytic case, that means that the function is 0. So, but yeah, no, this is a degenerate situation. Yeah. Okay, so what's the relationship between this global learning coefficient and the local one? But it's easy. The global one is the minimum of the local one. So this is saying that this is saying something about the concentration of this integral. This is saying that asymptotically these integrals, I mean the volume and the exponential integral, they will concentrate around the set of most degenerate singularity. So. And in fact, so this quantity, it will be maybe clear on this picture. So let's look at this situation. So here for this function, W0 is the union of the x and the y axis. And what's happening here is that on one axis the learning coefficient is 1/4. And on the other axis, it's 1/2 except at the origin. And the axis where it's 1/4 is this one, and this is where asymptotically I guess asymptotically goes this way, right? This is epsilon going to 0. Most of the volume concentrate along this axis. And along the other axis, the local learning coefficient is 1/2, 1/2, 1/2, 1/2, and then it drops when it goes to the origin. And this is the typical behavior.
It's like an inductive bias for one of the axes.
Yeah. And yeah, this is a picture with instead of some volume, some Laplace type integral. And finally, maybe I'll just comment on this one. This is basically, you look at this function, and this is the case where the W0 consists on one point and a curve. But actually, most of the integral concentrates just on the point and not on the curve, because the local learning coefficient here is smaller than the one here.
Remind us of the plot.
Yeah, it's this type of integral.
LW is the true loss at W, and in some weight setting W.
Is the population loss in?
Population loss. And then N is the amount of data.
Yes. What at least, I mean, this applies basically to any analytic function and with some appropriate assumptions. So it's yeah. This is a general statement about analysis. This has nothing to do with statistics, but well, it's a generalization of the Laplace. I mean, the Laplace approximation is the version for non-degenerate functions, or typically. Yeah.
Can you remind me why we care about the little plot angle? Like how that is a generalization error or something else?
Yeah. Well, it relates to the posterior, right? Because for instance, the partition function, so the constant in the Bayesian, is this, but with L replaced by Ln.
Okay, so this is something that it's an integral that looks vaguely like
Yeah, well, because it's possible to use that one to study the Bayesian one. Yeah. Okay, so let me try to discuss, or maybe let me pause for questions before I go into the results.
So this Laplace trick, it's like I can either think of changing epsilon and seeing how it broadens, or I can think about adding more data and seeing how it concentrates.
Yeah, it's just a different way to sort of probe this concentration. It's not so surprising. I mean, you can actually prove kind of directly that this, at least if you have two such sort of asymptotic behavior, the lambda has to be the same. That's not very deep, but yeah.
It might be easier to compute in a real situation, adding more data as opposed to trying to explore the.
Yeah, and in some sense that's what's happening in these applications of when you yeah. In some sense that's the idea behind this applied SLT method is maybe in some sense what you're interested in is the set of low loss parameter, but instead of doing that you sample from the local posterior. Yeah. Okay, so yeah, so this SLT is about statistical learning theory, and statistical learning theory in this talk, and so in this context of Watanabe, is really about the sort of large data limit, is the sort of asymptotic or frequentist properties in the large data limit. So theoretically, what the theory sort of, I mean, what the goal of the theory sort of gives an idea of the shape of the Bayesian posterior as it concentrates around W0. But more concretely, it's formulas so asymptotic formulas for the free energy and for the generalization and training losses. And in practice, what you want and that's what leads to the applied SLT method is estimators of those quantity. You want to use that. You want to sort of reverse the theory to estimate things like the local learning coefficient from data. So yeah, so everything that I'm going to talk about is contained in these 2 books, and basically in this first book of Watanabe. But yeah, if you're interested in this topic, I recommend having a look and also reading maybe first some of his recent surveys of the theory, which give a good overview and don't require digging into those books immediately. Okay, there are some assumptions. I think I might just sorry, I'm a mathematician. I can't give a talk without some assumptions at some point. But they are, as I said, they're all negotiable. So I mean, the one that the hardest one to negotiate is the IID assumption. This is, I mean, there are probably reasonable extensions in non-IID cases, but it's kind of harder. But the rest, like things like compactness of the parameter space, or or conditions about the support of the distribution, I think it's called relatively. And okay, and realizability is somewhat negotiable, because so Watanabe has figured out ways to extend it to some cases. Okay, so basically the starting point is a relationship between L and Ln, or K and Kn, and that's exactly what lets you sort of use these results on asymptotic of exponential integral in the Bayesian story. Basically saying that K, so now we're in the realizable case, so you should think that K, in fact K and Kn, they are both kind of vanish along W0, but Kn has a lot more wiggles around the true population loss function, or population KL divergence. And the question is how you control this wiggling. And Watanabe has this kind of singular central limit theorem, basically, where the wiggling is controlled by something of this, I mean, order square root of k divided by square root of n, which converges to a Gaussian process. And here I'm sort of hiding an important point, is that these things are actually not are sort of distribution valued rather than honest thing. But let me not go too much into that. It doesn't matter so much, because at the end of the day you integrate them. So I mean, distributions are made to be integrated, so that's fine. So this is really a standard fact away from W0. So if you look at some region of parameter space really away from W0, this is basically the central limit theorem, but in sort of a functional form, which is sometimes called empirical process theory. But to do it on W0, or around W0, this requires the sort of geometric input comes in when you need resolution of singularities. But so the outcome of this is that this reduces the study of the Bayesian posterior to the study of the sort of annealed or Gibbs posterior, where you replace now the Ln by L and this Gaussian process Xi. So I'm not going to say very much at all about the Gaussian process Xi. I'm going to concentrate on the role of these integrals. It's just the integral of it's the normalization constant. Yeah. No, it's L for this L. Yeah.
For this like CLT to be like so small in estimating like how far from this group we are, you would like to have like some bounds on the Gaussian process.
Yeah. Well, so maybe the interesting thing is that it turns out that, well, maybe I'll come back to this in a second. Yeah. Okay, so this is a very bad cartoon picture, but this is my picture of what sort of the difference between the regular and the singular case for this difference between k and kn, right? So in both cases you have some kind of true distribution. W0 in this case is there's just a point in both cases. It's not very fancy, but kn is sort of adding a bit of wiggling. The effect of kn in the regular case is to take this parabola and to sort of add and to move a little bit the minimum. To move the minimum a little bit and to lower it a little bit. So basically, this sort of suggests what's going on. That asymptotically, this function kn will itself be quadratic and look more and more like k, and that's basically what explains the sort of statistical learning theory in the regular case, where in the singular case there is a lot more flat region, and what happens is that the Kn does wriggle, and you sort of have to take this wriggling. I mean, this wriggling looks, I mean, from a sort of the physicist, if you put the physicist hat on, which I shouldn't have a physicist hat, but it looks like a spin glass, like, I mean, what I would call a Gaussian process and what physicists call a spin glass. And there are many critical points, and this sort of effect persists as n goes to infinity, and it's kind of important to the learning theory.
You remind me what?
Yeah. K is just L minus the minimum. It's just to shift it so that it's 0 is the minimum. I mean, the minimum is at 0. It's also it's the expected KL divergence between the truth and the model. Yeah.
And so that you've drawn there for Kn, that's one sample, that's the Kn for a particular sample?
Yes. Yeah, exactly.
And if you average the Kn together, do you get K?
Yeah, if you average the Kn for all samples, you get K. Yeah.
Great.
Yes. Yeah, because yeah. 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 I'm not sure. Yeah. I'm not sure I follow. Yeah, let's talk about it. Okay, so so what is the Bayesian statistical learning theory about? I mean, somehow the zeroth order behavior is that the posterior concentrates, right? So on the very mild assumption, much milder than all these big assumptions that I put, the posterior concentrates around W0, so that's what statisticians call posterior consistency. And what controls this posterior concentration is the free energy. So if you take two regions of parameter space and you want to compare the posterior probability of U and V, you can put it in. You can compare the log probability, and you just get the difference of free energies. So for regular model, this is very well understood, and so in particular, there is this Bernstein-von Mises theorem, which tells you that the Bayesian posterior distribution is actually asymptotically a Gaussian of the right scale, and with the covariance which is given by the inverse of the Fisher information matrix at the minimum. So inverses of Fisher information matrix operation are a telltale sign that you should forget what you're doing and do SLT instead. So yeah, for singular model, the posterior is not asymptotically normal, and it sort of concentrates in sort of interesting ways around W0. Okay, and the main formula from this perspective of posterior concentration is the free energy formula. So this is saying that, so we take and here because we do this sort of local free energy, we can sort of apply the theory around a local minimum. So you take some neighborhood of a local minimum of the loss function, and so this is saying that the free energy asymptotically is, so there's n times the loss at that point, and then then there's a log n term which is controlled by the local learning coefficient. So one corollary of this is that for singular model, the posterior does not just concentrate around this W0; it actually concentrates around this most degenerate point for the same reason, basically, that this Laplace is concentrated around the most degenerate point. So okay, this is a little quick, and I mean, maybe to justify this would be a bit, but there is this general idea that in statistics, in Bayesian statistics, that this posterior concentration sort of reflects a kind of accuracy and complexity trade-off, so accuracy of the model and versus simplicity of the model, let's say. And so from this perspective, we can think of this local learning coefficient of measuring the model complexity at this point. Okay, and okay, they are lower the term, and in particular, the only thing I wanted to mention here is that this Gaussian process Xi and the prior that we have sort of been forgetting about only comes up in the constant order term with a complicated formula which I won't read. Right?
Again, what it implies that lambda measures complexity.
Yeah, it's a little. Yeah, it's a it's a little unclear how to make a good. Sorry. Yeah. If there is an obvious thing, my brain doesn't return it now, but. Yeah, that's sort of the. Yeah, you could say that one way to think of the local learning coefficient is kind of the effective dimension of the model, and I will maybe say why this is in a second. But yeah. Yeah. Yeah, exactly. Yeah, so that's one way to think that. Yeah, if you be, well, yeah, if you believe that effective dimension is something, or this effective dimension complexity are sort of related. Yeah, so because this lambda is not constant there can be this phenomenon of Bayesian phase transition, and maybe since this was well covered in Jesse's talk, I won't go into it, but this sort of opens the possibility of sort of competition between this accuracy and complexity, which in sort of a more complex way than for regular models. Okay, so then there is also a result for the. Now we want to talk about generalization, and there is a connection. The connection with generalization in the Bayesian case goes through the Bayesian generalization error. And yeah, the simplest way to say it is that the average generalization error is this sort of the irreducible error. I mean, you can't do better than this. Is the loss on the optimal thing, and then you have a lambda over n. Okay, and the theory also kind of tells you about the difference between the generalization and training and overfitting, but maybe I won't go into that. Okay, then maybe this is just to explain how you go. I mean, to explain very quickly how you go from this theory. Sorry. Yeah.
So, how for big neural nets, how small is lambda?
We don't know. Yeah, there are. I guess it's a multi-layered thing. First of all, we don't know. Secondly, it's not clear that there is a sort of a single well-defined value of lambda, in the sense that because n is now not infinity, right, or because we're not in the large data limit. You also, I mean, one thing that the theory sort of tells you is that for smaller values of n, the model can be there is kind of an effective model that can be more degenerate than the final true model. That's what the story of kind of Bayesian phase transition is about.
Just trying to put this together, I mean, lambda is always upper bound, right? One of the biggest things that you possibly have to be. Right?
No. D over 2. Yeah. No, I mean, so it's a good one, but it's one that is kind of we don't have certainly don't have a complete for that question. Okay, so as I said, one nice thing that the theory does for you, and that leads to these for instance these applications to the local learning coefficient and in practice, is that you can reverse the theory to compute lambda from data. And to do this, it turns out that it's not easy to do this directly from the free energy formula. And there is Watanabe developed this widely applicable Bayesian information criterion, this involved basically averaging the loss for this tempered Bayesian posterior that was mentioned. Okay, maybe I want go to Rowan's talk to learn how to sample. I'm kind of running out of time, so let's see. I mean, I certainly don't have to I think I've said the most important things, but let me say a little more. Yeah, maybe. So just to show you a few more examples. And this example is maybe the kind of the more important one. So for theoretical purposes, it's quite important. It's the case where, well, let's discuss both. So this is the case where you have a sum of squares, but the number of squares is not equal to the dimension. In that case, it's equal to d prime over 2. And this situation is statistically corresponds to a so-called minimally singular models, and that does happen in some situations. A more theoretical example, but which is very important for the theory, is the case of monomial functions. So where you have a product of coordinate with even powers, just to have a non-negative function, and then it's equal to the minimum of the inverses of this thing. Yeah, then some elementary properties of the LLC. So first of all, it's a really invariant on the sort of analytic reparameterization. So what you should take out of this is it's a very robust invariant. It's not something like the spectrum of the Hessian or that is really scale dependent. It's kind of in some sense a very, very robust invariant of the degeneracies. Yeah, one way to compute it is using this kind of bounds. Yeah, if you kind of upper bound the function by some multiple of the same function on both sides, you get equality. And maybe I think I'll stop with this slide, and because I think this is a kind of an important point that and in my talk tomorrow I will maybe discuss this a bit more and try to think a bit more about this. So as we said, so the local learning coefficient is always less than d over 2, but in fact you have a better bound, which is that this is always less than the codimension of W0 divided by 2. So in general, as we said, this W0 is very big. It's not one point. It has very, very large families of points. And basically, the number of free parameters in this family, you can always subtract from the learning coefficient. So there is this extreme case. So he's gone, but there was this extreme case where it's equal to d over 2. Then in this case, it's actually a regular model. It's the case where the Hessian is. But what's kind of interesting is that so okay, there is a situation where the bound is attained, which is the so-called Morse-Bot function, or basically it's saying that the W0 is a manifold and the Hessian is transversely non-degenerate. So basically it look flat in one direction and quadratic in all the other directions. So in that case you get this, and that's this minimally singular cases. But in fact for many other functions, and in particular for deep linear networks, okay. I'll just finish my sentence. Yeah, that for deep linear network, it turns out that this is equal to this, and it's maybe the interesting question is how far in practice is this bound saturated for practical application. Thank you.